Welcome to All in All. Today we're embarking on an incredible deep dive into one of our solar system's most compelling planets.
Mars.
Mars. Always fascinating.
Absolutely. From its earliest tumultuous beginnings to its current sort of enigmatic state and even humanity's really grand plans for its future, we're going to explore Mars thoroughly.
Sounds like a great journey.
Yeah. Our mission today is to unpack its origin, really understand its profound significance to us here on Earth, trace its, well, dramatic evolution over billions of years, and consider its practical relevance for maybe humanity's next great leap.
It's a huge topic.
It is. Prepare for some truly surprising facts and I think profound insights into our nearest planetary neighbor. We'll be exploring how its story reflects possibilities for our own world and, our place in the cosmos.
It's true. Mars isn't just another dot in the sky, is it? Not just some astronomical curiosity. It's more like a cosmic mirror.
A mirror. How so? Well, it reflects fundamental principles of planetary formation, climate evolution, and even the very potential for life itself. We've got a stack of incredible sources today. Cutting-edge research papers, mission reports, even historical accounts and public opinion polls that'll help us piece together this really intricate story for you.
Okay, let's unpack this primordial story then, starting right at the beginning, Mars's birth. We're talking about the early solar system, this chaotic crucible of gas and dust and these nascent planetary bodies.
A very messy time.
Extremely messy. And our sources indicate that Mars formed its core and accreted most of its mass incredibly quickly, like within approximately 5 million years of the solar system's formation.
Yeah, that's astonishingly fast when you think about the time scale of the universe. Just a blink, really.
Right.
Indeed. That initial rapid growth phase, happening so fast in cosmic terms, was absolutely crucial for establishing Mars's foundational internal structure. But it wasn't the complete picture of its growth.
It took longer.
Yeah, the planet actually continued to accumulate material and grow for over 50 million years. So a substantially protracted accretion process after that initial burst.
50 million years. Okay, that's still pretty fast, but definitely longer.
Right. And this extended formation, it involved numerous pretty violent interactions between various protoplanets.
Protoplanets, like planetary building blocks.
Exactly. Think of them as planetary building blocks, some maybe moon-sized, some even larger. This whole period is often described as chaotic growth. It was like a cosmic demolition derby.
Huh. A demolition derby, I like that.
Yeah, where random collisions and, gravitational slingshot effects played an unavoidable role in shaping what Mars would ultimately become. It wasn't a neat linear process at all. It was a rough and tumble beginning.
That chaotic growth sounds absolutely brutal, like a celestial game of billiards with worlds as the balls.
Pretty much, yeah.
Yet I see here that understanding Mars's core formation, and therefore its earliest chemistry, relies heavily on something called the HFW signature.
Ah, yes. Hafnium tungsten.
What exactly is that, and what does it tell us about Mars's incredibly early chemical environment, especially considering such a violent birth?
Okay, so the hafnium tungsten, or HFW signature, it's basically like a geochemical fingerprint.
The fingerprint, okay.
Yeah, or a highly sensitive chronometer that scientists use to date the formation of planetary cores. And it's incredibly sensitive to the oxidation state of the material that accreted to form the planet.
Oxidation state. You mean like how much oxygen was floating around?
Sort of, yeah. Think of oxidation state as simply a measure of how much free oxygen or hydrogen was present in that early chemical soup. When we analyze Mars's HFW signature, it suggests a surprisingly narrow and consistent range for its early chemical environment.
Narrow and consistent, even with all that chaos.
Exactly. Specifically, it points to a redox state, roughly 1.3 to 1.6 log units below the iron-wustite buffer.
Okay, hang on. Below the iron-wustite buffer, what does that mean for us, the listeners? Can you paint a clearer picture?
Absolutely. Yeah. So imagine a chemical balancing point, right? The kind of neutral line for how oxidized or reduced a material is. The iron-wustite buffer is just a specific reference point in geochemistry that helps us define that balance.
Got it. Like a 0 point on a scale?
Kind of, yeah. So when we say Mars's environment was consistently below this buffer, it means the initial ingredients for Mars were formed under very specific conditions. It was consistently on the more oxygen-poor or reduced side of that chemical balance.
Interesting.
Yeah. And the profound insight here is that despite the violent, chaotic, cosmic demolition derby of its birth, including massive impacts from other protoplanets, Mars maintained a remarkably stable foundational chemistry.
Oh.
It suggests a resilience or maybe a fundamental chemical uniformity in the early solar system's building blocks that really shaped what Mars would become. What's particularly striking is that the HFW signature can even be matched for scenarios where large impactor cores merge directly with proto-Mars.
Whoa. So even giant chunks merging didn't throw it off too much.
Apparently not, chemically speaking. It demonstrates a truly complex and violent, yet chemically consistent, early history.
That's truly wild. So even with those massive chaotic impacts, the chemical environment remains surprisingly consistent. Okay, so a vital part of any young planet's protection, especially one that might become habitable, is a magnetic field.
Absolutely crucial.
Did early Mars possess this crucial shield, and how exactly would such a magnetic field form? What's its role?
Yes, it absolutely did. Early Mars likely had a protective magnetic field, much like Earth's.
Okay.
This field was generated by what we call a planetary dynamo, basically. Convective currents within its liquid iron-sulfur-hydrogen core.
Like dynamo.
Yeah.
Like in a generator.
Kind of the same principle, yeah.
Okay.
Imagine a giant swirling cauldron of molten metal deep inside the planet. As this liquid iron-rich material flows and moves because of differences in temperature and density, it generates electrical currents. And those currents, in turn, produce a magnetic field that extends far out into space. This magnetic shield would have been crucial for the planet's early environment. It acted like a planetary force field.
A force field against what?
Against the harsh, energetic particles streaming from the young sun, the solar winds. It provided a necessary defense, suggesting a very different and likely far more hospitable period in Mars's early history, shielded from the sterilizing effects of space radiation.
A protective magnetic bubble that sounds almost idyllic, like an early Eden. But, well, clearly it didn't last.
I don't know. Sadly not.
So the critical question becomes, what was the turning point? What fundamental changes occurred in Mars's core and then its atmosphere that transformed it from that potentially warm, wet world into the cold, barren landscape we see today?
Right.
Let's move into the dramatic evolution of Mars, from that warm, wet past to the cold, dry world we know.
Okay, that's a pivotal question. And it's really a story of internal changes with catastrophic external consequences. The magnetic field on Mars was, unfortunately, pretty short-lived.
How short-lived?
Well, our sources indicate that as the iron, sulfur, and hydrogen liquids in its core began to cool and fully separate, this process of differentiation, where denser materials sink and lighter ones rise, those vital convective currents that generated the field just
stopped. Why?
Imagine the molten core becoming less like a swirling dynamic fluid and more like a stratified, quieter liquid.
Yeah.
When those powerful currents stopped, the dynamo switched off, and the magnetic field vanished, probably within the first few 100 million years of Mars's existence, relatively quickly.
And that loss had catastrophic consequences, didn't it? Without that protective magnetosphere, Mars's atmosphere was just stripped away by solar winds.
Pretty much, yeah.
What exactly are solar winds, and how do they manage to tear away a whole atmosphere?
So solar winds are basically streams of charged particles, protons, electrons, alpha particles, continuously emitted from the sun's upper atmosphere. They travel at immense speeds, hundreds of kilometers per second. On Earth, our strong magnetic field deflects most of these particles around the planet, like a shield. But on Mars, with its magnetic field gone, these high-energy particles directly impacted the upper atmosphere.
Like cosmic sandblasting.
That's a great analogy, like a relentless sandblasting. Over billions of years, these energetic particles gradually stripped away Mars's atmospheric gases, especially the lighter ones like hydrogen and helium, which are easier to accelerate up to escape velocity.
So the light stuff goes first.
Right. Heavier elements were also affected, but the overall effect was this continuous erosion of the atmospheric blanket.
That's fascinating that the magnetic field just ceased. Makes me wonder about other planets. Like Venus also lacks a strong internal magnetosphere, right?
Correct.
Yet it has that incredibly thick atmosphere. What's the fundamental difference between Mars and Venus that allowed Venus to hold on to its gases while Mars lost so much?
That's a great comparative planetology question, and it really highlights the delicate balance of factors determining a planet's fate. The key difference lies primarily in gravity and escape velocity.
Ah, size matters.
Size and mass, yeah. Mars is significantly smaller than Venus, meaning it has a much lower gravitational pull. Its escape velocity, the speed an atom or molecule needs to achieve to break free from the planet's gravity, is also much lower.
Easier to escape.
Exactly. This made Mars far more vulnerable to atmospheric loss, especially during the sun's younger, more active phase. The young sun emitted much higher levels of ionizing radiation.
So the sun was more aggressive back then.
Oh yeah, much more active. That early aggressive sun was super efficient at stripping away Mars's thinly held gases. Venus, on the other hand, despite lacking a strong internal magnetosphere, is much larger and more massive.
So it has a stronger grip.
A much greater gravitational pull to hold onto its atmospheric gases. Plus, it has that dense carbon dioxide-rich atmosphere, which is harder to strip away compared to a hydrogen-rich one.
Interesting. Even Earth loses some atmosphere, doesn't it?
It does. Earth, despite its strong magnetic field, still loses hydrogen. This happens because water molecules in the upper atmosphere can be broken down into hydrogen and oxygen, and the lighter hydrogen can escape into space over time.
Okay.
But on Mars, the escape process for lighter gases like hydrogen and helium was much, much more rapid and catastrophic in its early history. It was that perfect storm. Lower gravity, a more active young sun, and the loss of its protective magnetic field.
So lower gravity, an aggressive young sun, and the magnetic field disappearing that completely changed the climate and the fate of water on Mars.
Absolutely. Transformed the planet.
What do we actually know about how wet Mars used to be before all these changes kicked in?
Well, billions of years ago, around the same time life was getting started here on Earth, Mars was a profoundly different place.
How different?
Scientific models, based on geological evidence we see today and atmospheric simulations, suggest it was much warmer and significantly wetter. It had a substantially thicker atmosphere.
Thick enough for liquid water.
Thick enough for liquid water to be stable on the surface, yeah. We're talking about a planet with freshwater lakes, maybe meandering rivers, and even warm, salty seas.
Seas. How much of the planet?
Estimates vary, but some models suggest these seas could have covered between 36% and an astonishing 75% of its surface.
The 75%, that's almost entirely covered in water.
I know. Imagine a Mars that looked less like a dusty red ball and more like a younger, smaller version of Earth, with vast bodies of water reflecting the sunlight.
It's hard to reconcile that image with the Mars we see today. So when did it start to become the cold, dry planet we observe? Was it sudden or gradual?
It seemed to have been a gradual, though pretty dramatic, decline. The degradation of habitability likely began from the mid-Hesperian period onward.
Which is when, roughly?
Roughly 3.5 to 2 billion years ago. This transformation was related to a combination of that relentless atmospheric loss we talked about.
Right. Thinning the air, dropping the temperature.
Exactly. And also impact erosion from asteroids and comets hitting the planet. These factors, working together over eons, contributed to the planet's irreversible shift to colder and drier conditions. It wasn't overnight, but a slow, inexorable march towards its current state.
And today, liquid water just can't exist on the surface, right? Pressure's too low, temperature's too frigid.
That's correct. Today, liquid water simply cannot persist on the surface. The atmospheric pressure is less than 1% of Earth's, and the average temperature is around minus 63 degrees Celsius.
So cold.
Yeah. Any exposed liquid water would immediately either freeze solid or, more commonly, sublimate, turn directly from ice into vapor.
So what happened to all that water, those ancient seas and rivers? Did it all just vanish into space along with the atmosphere?
Most of it didn't, actually. The vast majority of that ancient water exists almost exclusively as ice.
Ice? Where? Just the polar caps?
We find it in the polar caps, yes, obviously, but also significantly beneath the shallow subsurface, hidden from the harsh surface conditions.
Underground ice, how much are we talking?
A lot. What's truly remarkable is the sheer volume of this hidden ice. A vast amount of underground ice in just one region, called Utopia Planitia, is estimated to be equivalent to the volume of water in Lake Superior.
Wow, Lake Superior's worth of ice hidden underground. That's a mind-boggling amount, and certainly hopeful for future missions.
Definitely a key resource.
But you also mentioned earlier that the ancient surface waters were highly saline, potentially fatal to most Earth-like life.
Right. Evidence from Martian sandstones indicates that the ancient surface waters, the ones filling lakes and seas, did indeed have high salinity. Very salty.
How salty?
A level fatal to most Earth-like life we know today. Though it's possible some highly specialized extremophiles and microbes that thrive in extreme conditions could potentially survive or even flourish in such briny environments.
So the ancient seas might not have been friendly to life as we know it. What about the subsurface ice? Is it salty too?
That's a great question. Much of the subsurface ice is believed to be much purer, likely formed from ice sheets deposited when Mars's tilt was different, or perhaps from ancient snowfall. However, Some subsurface ice could certainly be mixed with salts, depending on its formation history.
So finding pure ice is key for future explorers.
Absolutely. Finding large reserves of relatively pure water ice will be critical. It can be melted and purified for drinking water, or broken down into hydrogen and oxygen for rocket fuel and breathable air. So, yes, ancient Mars was wet, but it wasn't necessarily universally hospitable in the way we typically think of Earth.
It's incredible how much a planet's surface can reveal about its past. Beyond the water, what geological processes etched Mars's surface? Let's talk about Valles Marineris, that huge canyon system. How does its story fit into this narrative?
Valles Marineris. It's an absolute titan among canyons, a real testament to Mars's dramatic geological past.
Just how big is it?
To give you a sense of scale, it's roughly 4,000 kilometers long, 200 kilometers wide, and up to 7 kilometers deep.
4,000 kilometers. That's about the distance across the United States.
Exactly, and it's vastly larger and deeper than Earth's Grand Canyon. This colossal feature stopped its main growth roughly 2 billion years ago, during that Hesperian period we mentioned.
And how did it form? Was it carved by water like the Grand Canyon?
Not primarily, no. It formed under immense stress from tectonic forces related to the Tharsis Bulge.
Yeah, Tharsis, that huge volcanic region.
Yeah, a truly enormous volcanic province on Mars. Imagine a massive planet-sized blister on Mars's crust. That's Tharsis, a region uplifted by volcanic activity. Its sheer weight and the stresses it exerted on the surrounding crust caused deep, parallel cracks to appear.
Ah, so it started as cracks.
Exactly, which then expanded and linked up over time into the magnificent canyon system we see today.
So these tectonic forces created these huge fractures from the Tharsis Bulge, and then I imagine water played a role in shaping it further, eroding those cracks.
Absolutely. Water definitely played a big part after the initial cracking. Early in Mars's history, after those cracks formed, water and melting subsurface ice escaped through these fractures, often in enormous quantities.
What did that lead to?
It led to ground collapse, creating what scientists call chaotic terrain regions, where the surface looks like it's literally crumbled into a jumble of blocks.
Chaotic terrain, I can picture that.
These collapses and the subsequent release of vast volumes of water led to massive floods, particularly at the eastern end of Valles Marineris.
Floods pouring out of the canyons.
Yeah, huge floods. And it wasn't just one single event. Evidence suggests they occurred in several stages during the Hesperian, pouring out of the canyons and into the northern lowlands, dramatically reshaping the Martian landscape.
Beyond those catastrophic floods, were there other, maybe more subtle erosional processes at work sculpting the canyons?
Yes, certainly. One significant process was sapping.
Sapping? What's that?
This involves groundwater emerging from the canyon walls, often through cracks and fissures. As the water flows out, it carries away loose sediment, gradually undermining the rock above.
So it eats away from below.
Kind of, yeah.
Yeah.
This process creates distinctive landforms, valleys that are typically round-headed, steep-sided, and branch out in a pattern resembling tree branches. It's a very specific signature of groundwater flow and erosion, quite different from surface runoff carving.
Interesting. And what about evidence from impacts? Do craters tell us anything about water or ice in the ground back then?
They do, and they provide powerful clues. Look at rampart craters.
Rampart craters?
Yeah, these are impact craters that have this distinctive sort of lobate, flower-like debris skirt extending outwards from the rim, often with an elevated ridge or rampart at its edge.
Okay, what does that tell us?
They are a strong indicator that the ground held substantial water or ice at the time of impact. The heat of the blast would have instantly melted or vaporized this subsurface water or ice.
Creating a sort of mud.
Exactly, creating a slurry of debris that flowed outwards like a liquid rather than just ejecting dry rock ballistically.
Okay.
This fluid-like flow lubricated the flying debris, allowing it to travel further and creating that characteristic splash pattern that forms the rampart, which can be, maybe 70 meters high.
Wow. So the crater shape itself screams wet ground.
It's a direct signature of subsurface ice or water, yeah.
That's a powerful clue. And Valles Marineris is also known for truly massive landslides, right? How did those contribute?
Oh, absolutely. Undermined cliffs and valley walls, weakened by the tectonic stresses and maybe water erosion, naturally led to enormous landslides. Some of these are truly colossal, stretching over 100 kilometers long.
100 kilometers? That's massive!
Imagine a single landslide stretching for over 60 miles. These colossal events weren't just spectacular, they were geological bulldozers, greatly widening the canyons as enormous blocks of rock slumped downwards.
Widening the canyons. And what's unique about them on Mars?
What's particularly interesting is that even Mars's thin atmosphere likely contributed to these flows. The extremely low atmospheric pressure means less air resistance.
Ah, so the debris travels further.
Yeah, allowing the debris within the landslide to travel further and faster than it might on Earth, where friction from denser air would slow it down more. It's a unique Martian phenomenon that helped sculpt these massive features.
And buried deep within these canyons, there are those mysterious layers, aren't there? The interior layer deposits.
Yes, the ILDs. They are truly one of the biggest enigmas of Valles Marineris. They are these mysterious sedimentary layers found deep within canyons like Melis Chasma and Candor Chasma.
What's mysterious about them?
Well, they're remarkably flat-lying and uncontorted, which suggests they accumulated in a geologically quiet environment, undisturbed by major tectonic activity. Scientists propose a few theories for their formation.
What?
They could be vast deposits of volcanic ash that fell from the sky over long periods. Or perhaps sediments that piled up in ancient lakes that once filled parts of the canyons. Their exact origin is still debated.
So they hold clues, but we don't know the full story yet.
Exactly. They hold invaluable clues about Mars's environmental history, but we're still working on deciphering them.
What about mineral clues, then? Do they tell us anything more definitive about the water history and how it changed?
They absolutely do. Minerals act like chemical fingerprints of past water interactions.
Okay, give me an example.
Well, the presence of olivine, a greenish mineral in some areas like Ganges Chasma, is significant. Olivine weathers very quickly when exposed to water, especially acidic water.
So finding it means?
Its presence suggests that these particular regions have experienced less water exposure over time, or at least less intense water interaction.
And the opposite. Minerals that show lots of water.
Right. Conversely, clay minerals, like those found in other parts of the canyon system, like Candor Chasma, tell a very different story. Clay minerals typically form through extensive weathering of rocks by water over long periods.
Okay, clays equal water.
Pretty much. And moreover, the type of clay minerals found indicates that the water involved in their formation was less acidic than the water that made rocks in other Martian regions we've studied.
Ah, so different kinds of watery environments.
Exactly. It suggests varied aqueous environments across the planet. Together, these mineralogical maps provide a complex mosaic of Mars's changing watery past.
It's truly incredible how much a planet's surface can reveal when we look closely. Okay, let's shift our gaze upwards to the atmosphere. Even though Mars's atmosphere is vastly different from Earth, so much thinner and colder, are there any surprising similarities in how it behaves?
Despite being about 100 times thinner than Earth's, studies of Mars's atmosphere do reveal fascinating similarities in atmospheric circulation and weather phenomena.
Like what?
For instance, we observe the significant effect of dust on global circulation, much like aerosols on Earth can influence our weather patterns. We also see the presence of baroclinic waves.
Baroclinic waves.
Yeah, these are large-scale atmospheric eddies, kind of like Earth's mid-latitude storms. They're driven by temperature differences and play a crucial role in redistributing heat and momentum around the planet, even in such a thin atmosphere.
So even with a tiny fraction of the air, the fundamental physics of weather still plays out in similar ways.
To a surprising extent, yes.
I've heard Martian global dust storms can be pretty intense, engulfing the whole planet sometimes.
They can be spectacular, yeah.
Do they offer any earthly parallels or insights?
They absolutely do. These Martian global dust storms even show parallels to sudden stratospheric warming events on Earth.
Sudden stratospheric warmings.
Yeah, these are dramatic, rapid temperature increases in Earth's stratosphere that can influence weather patterns across entire continents. Studying how energy is transported and redistributed during these massive Martian dust storms gives us invaluable insights into similar, albeit less dusty, processes here.
And connecting this to the bigger picture, thinking about planetary climates more broadly.
Well, the runaway greenhouse effect on Venus provides a really dramatic test case, doesn't it?
With its super hot surface and dense CO2 atmosphere.
Exactly. Temperatures hot enough to melt lead. It's a vivid natural laboratory for understanding how a planet's climate can spiral completely out of control. And it offers crucial insights into the potential long-term impacts of increasing atmospheric carbon dioxide here on Earth from, burning fossil fuels.
A stark cautionary tale from our cosmic neighborhood.
You could say that, yeah.
That's a powerful point, showing how studying our neighbors really can offer profound insights into our own planet's future. Which brings us squarely to the significance of Mars. Why does it truly matter to us here on Earth? Beyond just scientific curiosity, what's the real, tangible impact?
Well, one of the primary reasons, and perhaps the most understated one, is simply to understand our home planet, Earth, better.
Oh, so?
Mars is by far the most Earth-like planet in our solar system. That makes it an invaluable data point beyond Earth itself for comparative planetology.
A comparison point.
Right. By studying what happened to Mars's once warm, wet environment and its subsequent catastrophic climate shifts, we can gain critical insights into the complex interplay of Earth's own systems: surface, interior, atmosphere, hydrosphere, biosphere.
Understanding the balance here by seeing it broken there.
Precisely. It helps us understand the delicate balance that maintains habitability, giving us a clearer perspective on our own planet's vulnerabilities and helping us anticipate Earth's long-term future. It's like having a planetary sibling that took a very different path, allowing us to learn from its journey.
So Mars essentially acts as a unique laboratory for Earth's future, a natural experiment played out over billions of years.
You could put it that way, yes. Moreover, Mars offers unique geological conditions and data from its first billion years that are largely unavailable from Earth.
Why is that?
Here on Earth, plate tectonics, active volcanism, erosion, they've continuously recycled and altered our planet's surface over geological time. It's effectively erased much of its primordial record.
Wipe the slate clean, geologically speaking.
Pretty much. Mars, being much less geologically active today, has preserved vast stretches of its ancient surface. This allows us to study planetary evolution in a way we simply can't do on Earth. It gives us a clearer window into the early solar system.
And of course, the biggest question that always comes up when we talk about Mars: the search for life.
The ultimate question.
Is it a real possibility? And what are current missions specifically looking for?
The question of whether life emerged on Mars, especially during that early period when it was warm and wet billions of years ago, well, it's no longer just philosophy. It's now a discrete, scientific question we can directly address with our current technology.
So we can actually look for signs now.
Yes. Current missions, like the Perseverance and Curiosity rovers, are actively exploring for signs of past life, what we call biosignatures, or even potentially extant or currently existing life, particularly in the subsurface.
Why the subsurface?
We focus on the subsurface because any potential biosignatures there would be better preserved from the harsh radiation and oxidizing chemicals found right on the surface. The surface is a tough place.
What are the essential ingredients for life that scientists look for, and does Mars have them?
Okay, at a fundamental level, life as we know it needs three main things: water, essential nutrients, and an energy source for metabolism.
Water, nutrients, energy.
Got it. Mars clearly has water, mostly as ice, and strong evidence of past liquid water. In terms of essential nutrients, we look for the CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur.
CHNOPS?
Right. Mars has abundant water, so hydrogen and oxygen. We found readily available phosphate, phosphorus, which is a key building block for DNA and cell membranes.
That sounds promising.
It is. Nitrate, which contains nitrogen, could also serve as a resource, maybe formed by thermal shock from impacts or volcanic lightning on ancient Mars. And for energy, early Mars likely had various chemical energy gradients that could potentially fuel microbial life, much like deep-sea vents do here on Earth.
So the raw ingredients seem to have been present, at least early on.
It looks that way, yes.
But I've also heard about some pretty severe challenges to present-day life on Mars. What are the major obstacles that make Mars's surface so inhospitable right now?
You're absolutely right. There are significant hurdles today. The Martian regolith, that's the loose surface material, basically Martian soil. It contains perchlorids. These are highly oxidizing chemicals, pretty toxic to most Earth organisms.
Toxic. Not good for life.
Generally not. Although some highly specialized Earth extremophiles can tolerate them, and a few can even use them as an energy source. But their widespread presence is a major challenge.
What else?
The high ionic strength of any potential liquid brines, meaning very high concentrations of dissolved salts, also severely limits microbial propagation, makes it hard for life to thrive.
Too salty.
Yeah. Furthermore, the extremely low atmospheric pressure, just 1 to 14 millibars, it makes surface habitability very challenging. Any exposed cell would likely dehydrate or even burst.
Wow.
Though some hardy Earth bacteria have shown limited growth at simulated Mars conditions, down to about 7 millibars, but it's not exactly a thriving environment.
In radiation.
And of course, the constant bombardment of cosmic radiation from space is a major sterilizing factor for anything right on the surface.
So life on the surface today is a really tough sell.
Extremely tough. Yeah.
But despite these harsh conditions, What about intriguing clues or potential biosignatures that have already been found? Maybe suggesting past life.
We have several, and they definitely fuel ongoing scientific debate and exploration.
Like what? From meteorites.
Exactly. Analysis of Martian meteorites found here on Earth, like Shergatti and Yamato 000593, has revealed features suggesting remnants of biofilms.
Biofilms, like slimy layers.
Kind of, yeah. Communities of microorganisms attached to surfaces. Or carbon-rich spheres, potentially formed by biotic activity. The Shergatti meteorite, for example, showed features indicative of pre-terrestrial aqueous alteration.
Meaning water altered it on Mars.
Exactly, altered by water on Mars before it landed on Earth. And some of those alterations look like they could potentially be biological.
That's incredible. Actual rocks from Mars holding potential signs of ancient life found here on Earth. What other clues have piqued scientists' interest?
Well, the Curiosity rover exploring Vera Rubin Ridge found these stick-like structures, and microtunnels have also been observed in Martian meteorites.
Stick-like structures and microtunnels.
Yeah. These are morphologically consistent with traces of biological activity on Earth. They look like ichnofossils.
Ichnofossils. Trace fossils, like footprints.
Kinda, yeah. They're not the fossilized body of an organism itself, but rather the trace or evidence of its activity, like microscopic burrows or feeding trails.
Wow.
In this context, we're talking about microscopic patterns that look exactly like what some ancient microbes might leave behind as they move through rock or sediment. Now, purely abiotic, non-biological explanations haven't been disproven yet.
Right, gotta be cautious.
Absolutely.
Yeah.
But they are tantalizing clues. It reminds me a bit of the famous Viking lander face on Mars image from the 70s.
Oh, yeah, I remember that. Turned out to be a rock formation.
Exactly, just a trick of light and shadow.
Mm.
But it showed how much we want to see signs something familiar. These new clues, the microtunnels and structures, are far more scientifically robust, though still requiring more evidence.
And what about those fascinating Martian geysers? I've heard theories connecting them to life.
Ah, yes, the seasonal CO2 and water eruptions from the southern polar ice cap, they're truly captivating.
How do they work?
As the Martian spring arrives, sunlight penetrates the semi-translucent ice layer, warming the ground underneath. This causes trapped CO2 ice to sublimate, rapidly turn straight to gas.
Building up pressure.
Exactly, creating pressure that blasts out in these geyser-like eruptions. It carries dark dust to the surface and forms distinctive dark dune spots and spider channels as the gas etches pathways under the ice.
And the life connection.
Some scientists propose these dark spots could actually be colonies of photosynthetic microorganisms.
Living under the ice.
Potentially, yeah. They suggest these microbes overwinter beneath the ice, and when spring arrives, absorb sunlight, warm their surroundings, accelerating the CO2 sublimation, and then emerge to the surface with the dust.
That's a wild idea. Is there evidence?
The rapid growth rate and distinct appearance of these spots are unusual for purely geological phenomena, leading some scientists to suggest a biological explanation. But it definitely remains a hypothesis, not proven.
I also recall hearing about a very recent rock discovery with the Perseverance rover that generated a lot of excitement.
Ah, you're probably thinking of the Chiava Falls rock.
Yes, that's it.
The Perseverance rover recently core sampled this rock in Jezero crater, and NASA designated it a potential biosignature.
Why potential?
Because of its elevated phosphate content. Phosphate, as we discussed, is a key building block of life essential for DNA, RNA, cell membranes.
So finding a concentration suggests biology.
It could. Finding it in concentrations that suggest biological activity would be a huge step. But, and this is critical, potential doesn't mean definitive proof.
Right. Needs more work.
Absolutely. Further, meticulous examination of this sample back here on Earth, once it's eventually returned, is needed for a definitive determination of its origin, whether it's biotic or abiotic.
And going way back to the original Viking lander data from the 1970s, they originally found no clear signs of life, but there's a new interpretation now, isn't there?
There is, and it's a classic example of how scientific understanding evolves over time. The Viking landers performed experiments designed to detect organic compounds and metabolic activity.
And the results were
Ambiguous at best, mostly interpreted as an absence of life or at least organic molecules. However, much later, in the early 2000s, rovers like Phoenix discovered that Martian soil, the regolith, contains those perchlorates we mentioned earlier.
The toxic chemicals.
Right. So scientists went back and reanalyzed the original Viking data using this new knowledge. And the reanalysis suggests that these perchlorates could have actually destroyed any organic compounds present in the soil when they were heated up during the original Viking experiment.
Destroyed the evidence.
Possibly, yes, producing byproducts that were then misinterpreted as an absence of organic material.
So Viking might have found organics but accidentally nuked them?
It's a distinct possibility. This revelation means the question of past organic compounds on Mars, and thus the possibility of past life, is not only wide open, but perhaps looks more promising than originally thought. It's a powerful reminder to never say never in science.
Absolutely. Okay, this whole endeavor beyond the fascinating science has broader benefits for us, doesn't it? Let's talk about the societal impacts of Mars exploration.
Oh, the societal impacts are profound and really far-reaching. Mars exploration is a powerful, almost unparalleled driver for inspiring students in STEM.
Science, technology, engineering, math.
Exactly. And even the arts, I'd argue. Programs and simulations run by NASA and others have inspired millions, connecting that natural curiosity kids have with the wonders of the universe.
Like that quote, "Wonder is the beginning of wisdom."
Precisely. Mars truly exemplifies this. Students, like you hear stories about kids like Rosea, who envisions herself as the first woman on Mars. They get deeply engaged by this prospect. They see Mars not just as a distant object, but as a tangible goal that connects to their studies and future careers.
Fostering a new generation of innovators.
Absolutely. Problem solvers.
That's a tangible impact right there. And beyond education, what about technological spin-offs? Do these extreme challenges of space exploration translate into benefits for everyday life here?
Absolutely, and often in completely unexpected ways. The challenges demand extreme ingenuity, right? Pushing the boundaries of what's possible. And that leads to innovations with dramatic, often unpredictable uses right here on Earth.
Examples.
Think about life support systems. Developing closed-loop systems that recycle every drop of water and every molecule of air for astronauts. That directly benefits efforts to create sustainable systems on Earth. Robotics, too, has seen massive leaps forward. Autonomous vehicles, precision instruments.
What about medicine?
Huge impacts in health and medicine. Technologies developed for space have found critical applications, like the portable ultrasound device tested on the International Space Station. It's now incredibly useful for astronauts, sure, but also for emergency personnel in remote areas on Earth.
Wow.
Even fields like transportation and the miniaturization of electronics benefit hugely. It's often compared to how massive investments in radar technology during World War II led unexpectedly to the microwave oven.
An unintended benefit.
Exactly, a benefit unintended from direct oven research. The same principle applies to Mars exploration. The solutions we create for space often solve problems we didn't even know we had on Earth.
So unforeseen benefits improving life here. And what about the broader economic impact and, say, national morale? Is Mars exploration a good investment for a country?
From an economic standpoint, investment in space programs, especially Mars exploration, has a tremendously positive impact. It stimulates high-tech industries, creates high-paying jobs across diverse sectors, and drives innovation that fuels the economy.
And defense?
It's also critical for national defense, as space technology underpins many modern defense capabilities. Beyond economics, though, it fosters national prestige and unity.
Do people support it?
Public opinion polls consistently show strong support. For instance, one poll showed 75% of Americans supporting increasing NASA's budget to 1% of the national budget for a Mars mission.
1% for Mars.
And an even higher 84% support human missions if definitive life is found there. Mars truly excites the public, especially young people. It strengthens the economy and I think elevates the human spirit. It serves as a truly great goal for society, uniting us in a shared, ambitious endeavor.
It sounds like it's a unifying force. Does it also contribute to addressing global challenges and fostering international cooperation? Space seems like it demands collaboration.
Absolutely. Space exploration capabilities and the partnerships required to achieve them contribute directly to addressing global challenges. And they foster trust and diplomacy between nations.
How so?
Well, when countries collaborate on complex, expensive, and risky ventures like Mars missions, it builds bridges and creates shared goals that can transcend political differences. For example, it advances international preparedness for protecting Earth from catastrophic events like asteroid strikes.
Like that Chelyabinsk meteor in Russia.
Exactly. That event in 2013 injured over 1,000 people and was a stark reminder of our vulnerability. Mars missions also contribute to understanding and managing solar storms, which can damage electrical grids and satellites here, and developing means for space debris removal, a growing threat in orbit.
And the ISS is a good example.
International Space Station, yeah. It has already demonstrated the power of multilateral enterprises for scientific research and engineering collaboration. It's a successful model for future, even more ambitious Mars missions.
It's clear this is more than just science and tech. There's a profound cultural and philosophical impact, too, isn't there? That sense of wonder.
Indeed. Missions to Mars offer this unique perspective on humanity's place in the universe. They satisfy that deep, innate curiosity that has driven us since we first looked up at the stars.
Asking the big questions.
Right. They compel us to address profound questions about the nature of the universe itself, whether humanity's destiny is bound only to Earth, and if we are truly unique in the cosmos.
Like that Earthrise photo from Apollo 8.
Exactly.
Yeah.
Iconic images like Earthrise profoundly altered human perception, showing us our pale blue dot so fragile, hanging in the vastness of space. As Stephen Hawking suggested, to confine our attention to terrestrial matters would be to limit the human spirit.
And we see it in pop culture, too.
Oh, constantly.
Yeah.
From movies like The Martian to National Geographic series bringing space into our living rooms, even historical events like the 1938 Orson Welles radio adaptation of The War of the Worlds.
Which caused a panic.
Right. It showed how deeply Mars can capture the public imagination, inspiring both awe and, well, sometimes fear.
So after exploring Mars's past, its present, its profound impact, it leads us to the practical relevance. Is the time for Mars truly now? Are we really on the cusp of this next great leap sending humans there?
You know, the dream of sending humans to Mars, imagined for centuries, has genuinely never been closer to reality.
Really? Why now?
There seems to be a convergence of factors. Technical readiness, meaning we have or are very close to having the necessary technologies. There's robust public engagement, more than ever before. And there's a growing political will across multiple nations and private entities.
So the stars are aligning, so to speak.
You could say that. NASA's Mars Exploration Program's strategic plan for 2023-2043 explicitly outlines goals not just for robotic exploration, but to specifically support human exploration.
What does that involve?
It includes expanding opportunities through frequent, smaller, lower-cost missions to build foundational knowledge, investing in infrastructure both in space and eventually on Mars, significantly reducing access costs through partnerships both international and commercial, and developing those advanced technologies crucial for long-duration human spaceflight.
That's incredibly exciting. So what specific groundwork is being laid right now for human exploration? What are the concrete steps bringing us closer?
This is where the really cool engineering comes in. Humanity has the capability, and some argue maybe even an obligation, to send humans to Mars. It's widely seen as the logical next step after returning to the moon with Artemis.
Building on moon experience.
Exactly. Building on the experience and technologies gained. We're developing advanced in-space technologies, not just the rockets, but the sophisticated systems allowing humans to live and work for months, even years, away from Earth.
Like life support.
Robust life support, yes. Recycling everything.
Yeah.
New methods for radiation shielding. Highly autonomous systems to minimize reliance on Earth support because of that communication delay.
And getting there. Big rockets.
Big rockets, but also things like on-orbit refueling. That's a potential game changer.
Refueling in space.
Yeah. Imagine building up large quantities of fuel in Earth orbit. It allows us to launch smaller, more efficient components from Earth and then assemble and fuel them up in space for the long haul to Mars, like cosmic gas stations.
Making the trip more feasible.
Far more feasible and economical, potentially.
And beyond traditional rockets, I hear about more advanced concepts like nuclear thermal propulsion.
You're right. That's another potentially revolutionary technology, nuclear thermal propulsion, or NTP.
How does that work?
It aims to significantly cut down transit times. Instead of just burning chemical propellants, NTP uses a compact nuclear reactor to heat hydrogen to extreme temperatures, expelling it at incredible speeds to generate thrust.
The faster travel times.
Much faster. It could potentially slash transit times to Mars from, say, 7 to 9 months down to just 3 or 4 months.
Wow, half the time.
Which massively reduces astronauts' radiation exposure and the physiological risks of long spaceflight. And these aren't just sci-fi concepts. These are technologies being actively prototyped and tested now.
Incredible ingenuity. And once astronauts arrive, how critical are Mars's own resources? Can they live off the land?
Resource utilization on Mars in situ resource utilization, or ISRU, is absolutely key. It's essential.
Using what's already there.
Exactly. Rather than hauling everything from Earth, which would be prohibitively expensive and complex, mapping subsurface ice, for example, is critical for future explorers.
For water, oxygen, fuel.
Precisely. They'll need that water not just for drinking, but for producing oxygen to breathe, and crucially for making rocket fuel hydrogen and oxygen for the return journey. This highlights the immense logistics involved, not just the strategy. It's about engineering a self-sufficient outpost.
And we're talking about bringing actual samples back to Earth too, right? That must be a huge undertaking.
It is indeed. The Perseverance rover is currently collecting rock and soil samples from Jezero Crater, that ancient lakebed site.
Highly promising for past life signs.
Exactly. These samples are being carefully cached for eventual return to Earth, probably in the mid to late 2030s, in a joint effort with the European Space Agency, ESA.
Why bring them back?
These samples are critical for studying potential past life, with far more sophisticated laboratory equipment than we can possibly send to Mars. They're also vital for learning about Mars's older surface geology, offering that pristine early solar system record.
And what about future robotic missions? Will they continue to pave the way, maybe drilling deeper?
That's exactly the plan. For instance, ESA's Rosalind Franklin rover, part of the ExoMars program, slated for launch around 2028. That represents a significant leap.
Oh, so?
It will drill 200 centimeters, that's about 6.5 feet below the surface, much deeper than current rovers like Perseverance, whose drill only goes down a few inches.
Why drill so deep?
This deeper drilling is crucial for searching for organic molecules and biosignatures because the surface is constantly bombarded by radiation, which degrades organic material. Going deeper gets us below that radiation sterilization zone, vastly increasing our chances of finding preserved evidence of past life. The whole ExoMars program is focused on this.
But human missions, as amazing as they sound, come with immense challenges and risks, don't they?
Oh, absolutely. These are not trivial challenges. They represent some of the most significant engineering and medical hurdles we've ever faced.
Like radiation.
Radiation is a major concern, yes. Long-duration missions expose humans to both solar particle events and galactic cosmic rays. Both pose significant cancer risks, potential damage to the central nervous system, other issues.
So we need better shielding?
Better shielding, yes, maybe using water, or even the Martian regolith itself packed around habitats, and advanced medical treatments to mitigate the effects.
And what about the low gravity?
That's another big one. Mars' gravity is just over double the Moon's, about 38% of Earth's. Prolonged exposure can cause severe bone density loss, muscle atrophy, cardiovascular issues.
Can we create artificial gravity?
Some suggest rotating space habitats could provide artificial gravity during the transit to Mars. But you can't really do that effectively on Mars' surface itself. So adapting to and mitigating the effects of long-term low-G living is crucial.
And the Martian environment itself, the atmosphere, the dust?
It's formidable. Mars's atmosphere, while thin, is functionally a vacuum for humans. You can't breathe it. Minimal radiation protection. Yet it's dense enough to whip up massive planet-wide dust storms.
Dust storms sound bad for equipment.
They can damage equipment, clog solar panels, pose a respiratory hazard if any gets into habitats. So humans will need to live in advanced, sealed habitats, protecting them and maintaining Earth-like conditions inside.
And terraforming, making Mars Earth-like.
Yeah, terraforming Mars. Attempting to create an Earth-like atmosphere. That's just not possible with present-day technology. Mars simply doesn't have enough accessible CO2 or other greenhouse gases to create a thick atmosphere, and we lack the energy to release and sustain it even if it did. That's firmly in the realm of science fiction for now.
So the risks are immense. Radiation, low gravity, dust storms. Some call sending humans to Mars the highest risk endeavor ever attempted. Is it truly worth it?
It's true. It likely is the highest risk endeavor ever attempted by human explorers. It will require incredible leadership, teamwork, resilience, and an unwavering focus on safety and problem solving. Every contingency needs planning.
But the payoff?
But many believe the potential rewards for science, for technology, for inspiration, for the sheer elevation of the human spirit are absolutely worth that risk. It pushes our boundaries, compels us to solve problems that ultimately benefit life right here on Earth.
There's also this ongoing debate. Should we focus on settling Mars's surface, or are space habitats like those large rotating stations a more feasible or beneficial path for expanding beyond Earth?
It's a very valid and active discussion, with good arguments on both sides. Proponents of large space habitats argue they offer better control over critical factors like gravity. You could dial it in.
And radiation shielding.
Potentially easier radiation shielding, yeah. Maybe placing habitats in the shadow of asteroids or using thick layers of water or processed asteroid material. Atmospheric maintenance might also be simpler in a closed, artificial environment, so potentially safer and more hospitable than a planetary surface like Mars initially.
But Mars offers.
But planetary exploration offers direct access to a new world, right? A tangible destination. The powerful, deeply ingrained human inspiration of planting a flag on another planet. It connects to that primordial drive to explore, which carries unique psychological and cultural benefits a space station might not.
So it's not necessarily either.
Not necessarily, no. It's a question of where we prioritize resources and effort in the long run. Maybe both play a role.
So whether on the surface or in orbit, what's the path forward to actually achieve these human missions to Mars? What are the absolute non-negotiables?
Achieving human missions requires several crucial elements, sustained over time.
Yeah.
Continued significant investment in these advanced technologies we've discussed. Strong international partnerships to share the immense costs and risks. No single nation is likely to do it alone easily.
And political will.
And most importantly, sustained political will across multiple administrations or governments over decades. This isn't a short-term project.
What about the argument that we should fix Earth first?
It's an argument you hear often. While some argue resources should be directed solely to problems on Earth, it's important to remember, as we've discussed, that space exploration contributes to solutions on Earth through technological spin-offs, innovations in medicine, materials, energy, resource management.
And inspiration.
And crucially, it inspires the next generation of scientists and engineers who will be vital for solving future challenges, both here on Earth and potentially beyond. The Mars generation isn't just about reaching another planet. It's about pushing the boundaries of what we know and what we can achieve as a species. It's really about being poised to create a better future.
Mars. From its ancient past as a potentially life-sustaining world to its current barren beauty, and now as the focus of humanity's deepest aspirations, it just continues to captivate us.
It really does.
It's a testament to our enduring curiosity, our relentless drive to explore the unknown, and our incredible capacity for ingenuity. The red planet stands as this profound reminder of planetary evolution's power and, maybe, the delicate balance that allows life like ours to flourish.
Indeed. And as we reflect on Mars's journey, maybe consider this. How might the discovery of definitive evidence of past or even present life on Mars fundamentally reshape our understanding of our place in the universe?
How would it change things?
It would change everything. Our understanding of the origins of life itself, not just on other planets, but here on Earth too. It would compel us to reevaluate how unique or perhaps how common life truly is in this vast cosmos. It's a question that cuts right to the core of who we are.
A profound thought to end on. Thanks for listening to All in All.